Hello and welcome. Have you ever stopped to think why the world isn't just, well, a sort of random fog of individual atoms floating about? It's a really fundamental question, isn't it? Why do things stick together? Well, today we're going on a bit of a scientific detective journey to figure out the forces that literally bind our world together.
Right then. So this is the central mystery we're trying to solve. You see, under normal conditions, it's really only the noble gases, helium, neon, that are happy to just exist as single independent atoms. Pretty much everything else, from the oxygen we're breathing right now to the water in our cups, is made of atoms that have decided to team up. So what is this powerful glue holding them all together? That glue is what we call a chemical bond. But hold on, it's not some kind of cosmic superglue. It's actually a process driven by one of the most basic rules in the entire universe. Everything wants to get to a lower energy state. The best way to think about it is like a ball rolling downhill. It's not going to stop halfway. It's going to keep rolling until it reaches the bottom, its most stable spot. For atoms, bonding is their way of rolling downhill to find that comfortable, stable, low energy state. All right, section 1, the atomic social club, the quest for the perfect electron arrangement. So to really get a grip on this quest for stability, we need to understand what atoms think is the ideal state to be in. Let's imagine it's a bit like an exclusive social club, where only the most stable, most sorted elements are allowed in. The first big clue in this mystery came way back in 1916 from two chemists, Cosell and Lewis. They noticed that the noble gases, those famously standoffish and stable elements, all had one thing in common, exactly 8 electrons in their outer shell. This was a huge breakthrough. It led to something called the octet rule, the simple idea that all the other atoms are just trying to bond in a way that gets them that perfect octet, that golden ticket into the stable noble gas club. So, how does an atom actually get into this exclusive club? Well, it turns out there are two main ways to do it. First up, you've got ionic bonding. This is basically a transaction. One atom just gives away an electron, and another one snaps it up. Easy. Then there's covalent bonding. This is much more of a partnership. Two atoms decide to team up and share electrons to make sure they both get to feel like they have a full set.
Let's see this in action, shall we? Take table salt, sodium chloride. The sodium atom has just one lonely electron in its outer shell, and it's absolutely desperate to get rid of it. Meanwhile, chlorine has 7 and is just 1 electron away from that magic number 8. So it's a perfect match. Sodium just hands over its electron to chlorine. Now sodium is positive, chlorine is negative, and that attraction is what holds them together. But what about a chlorine molecule? Well, here you have 2 chlorine atoms, and they both need 1 more electron. Neither is going to give one up, so they compromise. They each share 1 electron with the other, forming a really strong covalent bond where they both get to pretend they have a full octet. Clever, eh? Okay, next section. The octet rule crumbles when the simplest rule isn't enough. So, the octet rule is wonderfully simple, isn't it? And it explains so much. But as scientists kept looking, they started finding all these weird cases where this neat, elegant rule just fell apart. The detective story was definitely not over yet. And yeah, the cracks really started to show. You've got atoms like boron, which in boron trichloride is perfectly happy with only 6 electrons, not 8. Then you have these other big atoms, like sulfur and sulfur hexafluoride, that can have an expanded octet with 10 or even 12 electrons. And don't even get me started on odd electron molecules, like nitric oxide. It's just mathematically impossible for everyone to get 8. The rule just doesn't work for them. But honestly, the biggest, most gaping hole in the octet rule is shape. It tells you which atoms are bonded together, sure, but it tells you absolutely nothing about the molecule's 3D structure. And in chemistry, believe me, shape is everything. So why is a water molecule bent, but a carbon dioxide molecule is a perfectly straight line? The octet rule has no answer. It's totally silent. We clearly needed a new theory. All right, on to the next piece of the puzzle. Molecules have shapes, the simple idea of electron repulsion. So this is where our next theory comes into play. And it doesn't just toss out the old ideas. Instead, it adds a crucial new layer, geometry. And it all boils down to one incredibly simple idea. It's called VSEPR theory. Yeah, I know, it's a mouthful. It stands for valence shell electron pair repulsion. The name might sound super complicated, but the core idea is just brilliantly simple. Think about it. Electron pairs in that outer shell are all negatively charged. What do like charges do? They repel. So they're going to naturally arrange themselves in 3D space to get as far away from each other as they possibly can. It's like having a few guests at a party who really can't stand each other.
They're not going to huddle in the middle, are they? No, they'll each go to a different corner of the room.
And this one simple rule of repulsion lets us predict the basic geometry of molecules with, honestly, incredible accuracy. If a central atom has two electron pairs pushing each other away, the furthest they can get is 180 degrees apart, a straight line. If there are three pairs, they'll form a flat triangle, a trigonal planar shape. And with four pairs, they point to the corners of a tetrahedron. It's so elegant and it's just so powerful.
But wait, there's a crucial twist. It turns out not all electron pairs are created equal. You've got bonding pairs, which are tied up in a bond between two atoms, and then you have lone pairs, which belong only to that central atom. And these lone pairs, well, they're held in a bit tighter, which means they take up more space, and they push everything else away much more forcefully. You can think of them as the bullies of the molecular world.
You can see this effect so clearly when you compare two molecules. Let's look at methane. It has 4 electron pairs. All of them are bonding pairs, no bullies. The result? A perfect, symmetrical, tetrahedral shape. But now, look at ammonia. It also has 4 electron pairs in total, but one of them is a lone pair, our bully. And its powerful repulsion literally squashes the other 3 bonds down and closer together, changing the shape into what we call trigonal pyramidal and making that bond angle just a little bit smaller.
Okay, next up, the architecture of bonds, how atoms actually build these shapes. So VSEPR theory is absolutely fantastic for predicting the final shape, but it's still just a model based on repulsion. It doesn't really explain how an atom's own orbitals, the s and p orbitals we all learn about, actually manage to form these exact shapes. To get that answer, we need to look at the very architecture of the bonds themselves.
And this is where something called valence bond theory enters the picture. And again, it doesn't replace VSEPR, it actually explains it. It gives us the how, the underlying mechanism, and it does it through this really beautiful idea called hybridization.
Let's go back to our friend methane. A normal carbon atom has 1 round s orbital and 3 dumbbell-shaped p orbitals, and they're all at 90 degrees to each other. Now, there's just no way those can make a tetrahedron. So the atom does this little bit of quantum magic. It hybridizes them. It's just like a builder mixing sand and cement together to make concrete, a totally new material perfect for the job. The carbon atom mixes its 1s and 3 p orbitals, and it creates 4 brand new identical orbitals. We call them sp3 hybrids. And what do you know? These 4 new orbitals point perfectly to the corners of a tetrahedron, all ready to form nice, strong bonds.
Okay, section 4. A deeper understanding, choosing the right tool for the job. Right, we've come a long way, haven't we? From the simple octet rule to VSEPR shapes and now valence bond theory's mechanics. You can really see how science works. It builds on itself, creating a more and more detailed picture. It's not that one theory is right and the old one is wrong. It's about having a whole toolkit and knowing which tool to use for which job. And for the really, really fine details, scientists have an even more powerful tool in their box: molecular orbital theory. Now, this one is much more complex mathematically, but it looks at the whole molecule as a single system. And because of that, it can explain some really subtle things that the other theories just can't touch. For example, did you know liquid oxygen is actually attracted to a magnet? It's called being paramagnetic. It's super weird, especially since it has an even number of electrons, but MO theory explains it perfectly. So there we have it, our complete scientific toolkit for understanding bonds. If you just want to know what's bonded to what, Lewis theory is your go-to. If you need to know the 3D shape, you pull out VSEPR theory. If you want to know how it makes that shape, you look to valence bond theory. And if you need all the nitty-gritty details about energy and magnetism, you bring in the big guns, molecular orbital theory, a different tool for every question. When you think about it, this whole journey through bonding theories really just mirrors our journey into understanding the atom itself. As our picture of the atom got more and more sophisticated, going from simple electron shells to complex quantum orbitals, our ideas about how those atoms stick together had to evolve right alongside. The two are completely intertwined. You really can't understand one without the other. And that really brings us to a final thought. We've seen how each of these theories is like a different lens, each one more powerful than the last, letting us peer deeper into the molecular world and see things we couldn't before. It really makes you wonder, doesn't it? What other secrets are these molecules hiding? What mysteries are just sitting there, waiting for us to invent the next, even more powerful lens to finally bring them into focus? Thanks so much for joining me.